Alright, for today's video, I want to do a quick exploration into the different, at least some of the different data types in Houdini, especially when you're working with Vex, and what they are, and why you would want to use one over the other. I realize I never really kind of went into this, and it's definitely something that is worth exploring at a foundational level. So, the first thing that I want to get kind of addressed is what we mean by a data type. I like to think of data types as containers, um, in the sense that the variable or the attribute or whatever it is that we're dealing with, that's going to contain some information, and then the data type is like a label on the outside of the container that says what kind of information is being uh, held in that container. Uh, so, for example, when we talk about a point's position, we might use a vector data type to describe that information. Um, when we're talking about maybe uh, the number of spheres that you have in a simulation, uh, it might be more useful to use an integer data type. And so basically think of data types as you've got these containers of information, and the data type is like a little label on the outside that says what you're going to find in this container is this type of data. Okay? So the first one we'll talk about is integers. Now, integers, it's a mathematical concept, and um, uh, it's basically any number that is not um, that uh, it, the mathematical definition is actually a little bit difficult to articulate. I'm gonna attempt to. Um, I'm gonna do a quick Google search and see what Google has for it. Um, so they say integer is a whole number, a number that is not a fraction. So I think the easiest way to think about integers is for me to just say a few of them. Like, for example, -1 is an integer. +2 is an integer. 5 is an integer. 10. You know, 2.5, now all of a sudden that's not an integer anymore. And so what's the big deal about integers? Why do we need them? Well, if you have a situation where a lot of times when you're counting things, it makes sense to use an integer, right? If I wanted to keep track of how many spheres I have 5 by 5, so I have 25 spheres. So it wouldn't make sense to use um, like a decimal to describe that, right? I know it's going to be some whole number. So that would be an instance where I would want to use an integer data type, because I don't want like 2.5 spheres. That's not really useful way of describing that situation, right? I want to know, do I have 2 spheres or do I have 3 spheres, right? Or do I have 25? So that's kind of a situation where you would use an integer data type. And I'm going to, for each of these examples, I'm going to explain the data type, and then I'm going to give like a more concrete example of where you might find this in Vex. So um, a lot of times where you're going to find an integer data type a lot of the time is when you're doing your for loops, right? So a lot of times when you're following a tutorial and someone's doing something in Vex, they'll do this for int I equals 0 thing, right? And what's happening here is we're establishing a new variable I, and we're giving it a data type that is integer. And that's important because what are we actually doing with a for loop? We're repeating some instructions a certain number of times, and we don't want to repeat it 2.5 times. We don't want to repeat it 3 3/4 times. That would be confusing. Like, if I did a for loop that only ran 3.5 times, well, where's the halfway point? Like, where do we cut off, right? It doesn't make sense. It's not very useful to think about it in those terms. What is useful is to think about it as an integer, right? I'm going to run the loop 3 times. I'm going to run the loop 4 times. I'm going to run the loop 5 times. You see, an integer is a data type that makes a lot more sense in this case. So that's why, a lot of times you'll see tutorials, they do this for int I equals 0 thing. And you kind of just copy this down, and you don't really think anything of it, but it makes sense when you really kind of stop and consider what's going on here, right? We're establishing an integer, we're starting at 0, we're going to stop the loop once the integer has become less than 5. So what's less than 5? 4. So we're going to run it 0, 1, 2, 3, 4, and you can't see, but in my hand I'm actually holding 5 fingers, right? Because if we start counting at 0 and stop at 4, that's actually 5 times through the process. I know it's a little confusing, but remember in computer science, a lot of times we start counting at 0. That's something that can really throw people off, but you'll get used to it the more you kind of deal with it. And then what this I++ does, it basically just, it's a really nice shorthand way of basically saying, once you go through the loop, go ahead and add 1 to that integer. So it was 0 the first time around, so now it'll be 2. I'm sorry, it'll be 1 the next time around, and then 3, and then so on and so on. So I just have a simple little bit of code here that says, hey, if your point number, now that's another one that makes sense to be an integer, right? If we look at, see, these are the point numbers right here. It doesn't make sense to talk about, oh, what about 0.2 and a half? Like, there is no 0.2 and a half, right? There's 0.2 and there's 0.3 in our geometry. There's no 0.2 and a half. This isn't Hogwarts. There's no platform 9 3/4. Even though I love that that world and the whimsical nature of platform 9 3/4, in Houdini, if we had 0.9 3/4 for describing a point number, we would get wildly unpredictable results. So you see these data types help us kind of organize, what it is that we're kind of dealing with. So for point numbers, that's another one where these need to be whole numbers. I need to start at 0. I need to go to 1, 2, 3, 4. I don't need to see a 3.5 between 3 and 4. That's just going to be confusing. So point number is like another data type that makes sense to be an integer. So basically I'm just saying if your point number can be divided by 2 evenly, that's kind of what this expression means. I can get into the math behind it, but I don't really want to do it for this particular video. Then go ahead and add 1 to your y position. So if you notice, what happens here is every other sphere actually got moved up 5 units in space because I ran the loop 5 times. But just a quick example of some common places where you would run into an integer in Houdini. So the next example that we're going to talk about is the string data type. A string data type is a type of data that we use a lot as humans in our everyday life, but we don't tend to use it a lot in visual effects. In visual effects, most of the data that we're dealing with actually tends to be numbers, right? Even things that we as humans describe as with words in visual effects a lot of times are described as numbers. We'll kind of see an example of that in a little bit, but to kind of put it shortly, a string is, you could think of it as like a word. Now I'm an English speaker, so I think of it as a word in the English language, but it could be a word in any language, right? It's just kind of like a series of letters strung together to create some sort of meaning, right? So strings, computers tend to not really, unless you're talking about like an AI or something like that, computers, sometimes they have a hard time really doing anything useful with strings. Like, for the most part, at least I'm talking strictly in the visual effects world, a lot of times numbers are going to be easier for your computer to kind of process and do cool things with. But just to kind of show an example, I have a set of boxes here, and basically I created a string attribute and I called it color, and I basically just went through and I gave every single point, depending on which box it was, a color attribute. Now, what I want to make very crystal clear is that just because this point has a string attribute named color that says turquoise, that's not what's making the box turquoise, okay? What's making the box turquoise is this information here, this RGB color data here. Okay, so for a computer, this is what it sees as color information. This is more, this is kind of like almost for humans, um, in the sense that maybe I want a string attribute to like keep track of like a group. A group is like a good example. So a lot of times when you're building geometry in Houdini, sometimes you'll, like for example, if you're going to rig something, sometimes it's helpful to um, put some points in different groups. So you might have like the head group or like the neck group or the spine. And so, you know, in that scenario, you see how it becomes very useful to start describing things with words like the spine group or the head group, right? So in that instance, a string data type would make the most sense there. Um, but like I say, strings, you won't run into them as often as the other data types. But it is important to mention them. The other thing about strings is they need to go in either single quotes or double quotes. I think both will work equally well in every situation, but I'm not 100% sure about that. I tend to be a double quotes guy. I've seen a lot of people who use single quotes, but I come from a background where a lot of times uh, single quotes will do something different than double quotes, so I just kind of got used to building strings with double quotes. So that's why you'll see me do that in a lot of my tutorials. But I don't want it to be confusing. Single quotes will work just as well. So that's the example of strings. So now we'll get into vectors. So vectors, I think, as far as if you're talking about visual effects, I think vectors is probably the most common data type that you will run into. And it's also unfortunate that they also kind of happen to be the most complicated in many ways. So a vector, if we go back to that container analogy, so a container that's holding a string data type or an integer data type, it's kind of just like a normal box. Like a normal box, there's really nothing special about it. A vector, at least the most common vector type that we use in Houdini, is called a vector 3. Now, because a vector 3 is so common in Houdini, we actually just call it straight up a vector. So when you see vector in Houdini, you're talking about a vector 3. Okay? And the way I think of a vector is it's a container that's kind of like a bento box, right? So if you've never had the pleasure of having a bento box lunch, it's one of my favorite foods. And basically, the way it works is you've got these neat little compartments that kind of organize your food. Here's a good example right here. So within the data type that is bento box, you see you have these nice compartments for, you've got some rice, you've got some sushi, looks like a crab wonton, very tasty. So when we talk about a vector 3 versus a vector 4 or a vector 2, we're talking about how many divisions, how many little compartments within that container that we have. So if we have a vector 3, we're expecting to populate that container with 3 individual components, right? So that's why things like position and color are so nicely represented by vectors, because think about when we're talking about 3D animation, we're talking about 3D space, which a lot of times we represent as X, Y, and Z. Well, how many letters did I just list off there? 3, right? So a vector 3 is going to be perfect because we have space for the X component, we have a space for the Y component, and we have a space for the Z component, or the Z if you're not in the U.S. Um, so so that's really critical to understanding about vectors, right? Is that there's these kind of individual components. So when we talk about position, um, for example, um, if I look at this, let's actually look at this box here. So if I look at this box, the only information on it is we have a point number, which is going to be an integer data type, and then we have a vector here. Now, the way that vectors are shown in your geometry spreadsheet is that they're broken up into their different categories, right? So this is like the rice container, this is the sushi, and this is the wonton, right? But this entire thing here is the bento box, right? That's the vector right there. So, for example, for point number 0, it has a value of negative 0.25 in its rice container. It has a value of negative 0.25 in its sushi container, and it has a value of negative 0.25 in its crab wonton container. That's really sad. You have negative amounts of food. I would probably want to be this one right here, point number 6. He has everything, 0.25 rice, 0.25 sushi, and 0.25 crab wonton. But anyway, weird analogies aside, the point is that there are many instances in 3D, in the world of 3D, that it makes the most sense to use vectors as a data type. Another example is color, right? So now we can see that our box has color information. So how does the computer know what color to make this box? Well, it looks at the color attribute and it says, oh, perfect, I need an R, a G, and a B value, right? Red, green, and blue. So it looks in the bento box and it sees, in my rice container, I've got 1. In my sushi container, I've got 0.25. And in my crab wonton container, I've got 0.25. So the computer knows that these numbers in those containers mean this color, right? So if you have a value of 1 in the red channel, 0.25 in the green, and 0.25 in the blue, then that means that's this color here on the screen. So even though, to us humans, since we're inferior than computers, as proven by the Terminator franchise, we can only describe color. For example, if I go up to somebody on the street and I say, oh, the color of that is 0.643763, 0.123121, and 0.2365, they're going to look at me like I'm crazy, right? Like I've lost my mind. But to a computer, it would very clearly understand what you meant. For humans, we might call this magenta, right? That would be like a little bit more useful data type for us. But when we're interfacing with computers, it's more often that you're going to refer to color by its R, G, and B values. So we're going to use a vector there. Okay? So so I think position and color are like pretty straightforward vectors to work with once you kind of understand the idea that it's just a container that holds different components. But another vector that shows up a lot and that can be a little bit confusing is the normal, right? So if you're working with a piece of geometry that has normals, normals are also described as a vector. Now, it can be a little bit confusing about why this is, because if we look at, if I go to, for example, I'm going to focus on point number 5, okay, because I've kind of set up something here to kind of demonstrate what I want to get across. So if we look at point number 5, we can see that it has a normal, right, and it's of the data type vector. We know because here's our 3 little containers in our bento box, right? And if we look at 5, it says 0.57735 in the x component, 0.57735 in the y component, and negative 0.7735 in the z component, or the z component. Now, what took me a long time to understand is this does not mean that the normal is at this position. What's really, and this is a bit of a mind bender, but a vector is actually more similar to a direction than anything else. So even when we're talking about position, I know it's strange because if we say that a point is like, let's say we say that a point is at 1, 1, 1, so like 1 in the x, 1 in the y, and 1 in the z. Like, in fact, I'll do that. So let me put a sphere down here, and I will put its center at 1, 1, 1. So now, and let me make this a lot smaller. So now, if we look at our position, it's 1, 1, 1, right? And we can think of that, we can almost think of that as this sphere lives at 1, 1, 1. That's a useful way to think about it, but it's not exactly what's going on here. What's really happening is that this vector actually describes a direction from the origin, right? So in any 3D environment, there's a point of origin, right? In fact, let me actually make this a little bit easier to understand. I'm going to put 0 in the Z component, and I'm going to go to front viewpoint here. So with relation to 0, 0, you're just going to have to kind of trust me on this. 1 in the x direction and 1 in the y direction, it's almost like we have a force that's pushing in the positive x direction, right? And then we have a force that's pushing in the positive y direction. So if you think about it, if you have like, you know, let's say I'm standing at the origin. I'm standing here at 0, 0. And one person ties a rope around me and they start pulling in this direction, okay? And then another person ties a rope around me and starts pulling in this direction. I'm going to actually start moving in this direction, right? In a perfect diagonal, because this force it's kind of dragging me here, and then this force is kind of dragging me up, so it's kind of, I end up kind of splitting the difference, and I end up traveling in this direction. So the point being that these numbers with this vector represent a direction, okay, that points from the origin to this place in space. Okay, so that's how the computer knows to render this sphere here, is it starts at the origin and it looks and it says, 1 in the x, 1 in the y, 0 in the z. Okay, I know which direction that is. That's this direction. And I also know how far to go because of these values. If I want to go even further, or let's say I want to go less, I can put 0.5 in each of these, right? And see, now it knows to render the sphere right here. So you can think of these forces like tugging on something where everything starts at the origin. And it's just a matter of like, you have 3 forces acting on any point at any time in the x, y, and z direction. And depending on, like, for example, if I make the x direction stronger, notice how this person is kind of winning the tug-of-war game, right? I can make it more extreme, like I can make this force only 0.1. And you can see that in the x direction, this sphere, this guy must be a lot stronger than this guy, right? Because this tug-of-war, remember, if you think about it as starting at 0, 0, right? Starting at 0, 0, 0. This guy pulled it a lot further in his direction than this person was able to in the vertical. I could change that, right? I could make this 0.1, and then I could make the y guy stronger, right? So now it's tugging much harder in the y direction. So I know that's a little bit confusing, but I think it's really important to understand that vectors are a direction, and they also have something called a magnitude, which kind of refers to like how strong in that direction you're going. Okay, so you have a direction, and then how strong in that direction you're going. Okay, so if we look at my little example here with the normals, and we look at point number point number 5, then what this vector, what this bento box is basically doing is it's telling the point, hey, your normal direction, which is used for shading a lot of times, is this way, right? And what's nice about Houdini is it's got this nice, and most 3D softwares have this, you have a nice way to kind of show that information in the viewport. But to prove that it's a direction and not like, it's not like this normal is actually living at 0.57735, 0.55735, and negative 0.57735. That's not what's happening. This is showing a direction. To prove that, I've made a sphere that actually physically lives at that space, right? So I took this normal from point number 5, and I put those exact numbers in here. And notice what's going on. The normal is pointing to this place in space. Okay, it's pointing, so that further emphasizes my point that a vector is a direction. Okay, and what I can do is I can strengthen how strong that pull in that direction is by multiplying a vector. So if I multiply it by 2, you see it gets stronger, right? And if I multiply it by 3 altogether, I can make the normal reach this sphere. But I wanted to emphasize, I really want to emphasize that when we're talking about vectors, we're talking about a direction first and foremost, and then we're talking about a magnitude, or how much strength or how far in that direction the pull is, or the push, however you want to think about it. So anyway, and I did skip floats, and the reason I skipped floats is because I want to show you that I tricked you, because we've actually been using floats this whole time that we've been talking about vectors, because inside our individual components of our vector, so let's take for example our color vector, right? So these individual parts right here, these are floats, right? So float is basically just a number that has a decimal. So it's kind of the opposite of an integer, right? So it is things like 1.0 or 0.25 or 0.769, right? So you can think of lots of instances where you would want to use a float, right? I mean, there's too many to really think of. And to prove this to you, I will show you using a point VOP. Now, VOPs is basically just like a visual version of vex, but to prove it to you, so we already know that that position is a vector, right? And it has 3 components, right? So what I can do is I can do vector to float, and what that does is that takes an incoming vector and it splits it into its 3 float values, right? So I've kind of proven that the vector bento box, inside each of its containers, each of the individual food items is a float. But I could put anything in there. Like I could make a bento box that has integers in it, right? And that might be like an array or something like that. So we can kind of get a little bit more fancy with this stuff. But at a basic level, like what I can do, for example, is I can split the vector up into its 3 floats, and I can say, okay, let's go ahead and add 1. We'll take the y value, right, and we'll add 1 to it, right? And then what we need to do is we need to put this in the position. So we need to go back to a vector. So there's also the float to vector node, which this does the opposite, right? It takes 3 floats and then combines them into your bento box. So the way you think about it is the bento box comes in, it got split up into its individual pieces, right? Here's the rice, here's the sushi, here's the crab wonton. We did something to the sushi, hopefully we made it better, and now that sushi needs to go back into a new bento box, right? So I'm putting a float to vector, and I'm saying, okay, here's my new bento box. I'm going to use the rice from the old one. I'm going to use the new sushi, and then I'm going to use the crab wonton. Okay, now I made a new bento box, but I just changed some of the containers a little bit. And now I'm going to put that into the position, and I just moved everything up by 1, right? Because that's all I'm doing is I'm adding 1 to the y component of every point. So that's basically that. Now, another thing that was in your message that I want to address is why we use curly braces. And I think what you meant was, why do we use curly braces for vectors? It's a good question, and I'll try to explain it the best way that I can. I think that if you think about it in terms of these containers, we need the curly braces. So let's say I want to make a vector, right? And I'll call this position adjustment. Okay, and I'm going to go ahead and put 0 in the rice container. I'll put -2, or actually -1 in the sushi container, and I'll put 0 in the crab wonton container. So the curly brackets. Why the curly brackets? Well, this kind of tells us, like, this is the bento box, right? And these commas are like the individual separators. So if we bring back our bento box analogy, the curly braces kind of tell the computer, hey, I am giving you a bento box. Listen up. And then what the commas do is they tell you, okay, I'm done filling the rice container, and then time to move on to the sushi container. And then, oh, I filled that up. Time to move on to the crab wonton, right? So if we look at that, like, that's kind of what's going on here. So curly brackets says, hey computer, I got a bento box here for you. And I'm putting this in the first container, and this in the second, and this in the third. So now what I can do is I can add this vector that I made. This is a really inefficient way. I would never code it like this, but just for demonstrating purposes. And basically what I did is I kind of reverted the change that I did here, where I moved everything up 1. I just moved everything down 1, right? And I realize this is kind of an impractical, way of doing this, but I think it kind of at least illustrates my point. So that's kind of what the curly brackets are for. Now you might ask yourself, well, why don't you just use parentheses, right? That looks like a bento box to me. Well, the problem is we already use parentheses for other really important things. Like, for example, when we're dealing with an expression, right, or a function, like, for example, the point function, right? The point function takes so we need a geometry stream. We need an attribute. Let's take the color attribute, actually. And let's see. Actually, let's do this. Yeah, let's go. Let's make a new vector. We'll call it color, actually. And so all I've done basically is I've used the point expression to use the remember we a lot of these functions we start by telling which geometry stream to use. So we want to use the 0 stream, right, which is the first one, right? Again, the confusing thing, we start counting at 0. I know, but that's just the way it is. This is actually a good review because we're actually covering a lot of stuff here. Because we start with an integer. We start with which geometry stream you want to enter. It wouldn't make sense to say the 0.5 stream, right? We could use the first stream, we could use the second stream, or the third, but that needs to be an integer. It absolutely has to. It just doesn't make sense if it's not. So that's, and then for the attribute, the actual point attribute that we want to look at, we have names for these attributes. So here we're actually using a string data type, and that string has a name, and it's CD, and that stands for color. and then we need to know which point number to look at. So we're just going to use your own point number. So at PTNUM. But basically, where I was where I was going with all this was to say that if the parentheses help this function where it's going to start and where it's going to end, right? It says, hey, I know point function. I know you need some directions. You need some stuff to do your thing. So I'm going to give you a parentheses and say, hey, we're going to start with your instructions, right? First, we're going to give you a 0, and the point function knows that, okay, the first thing that my programmer gives me is the data stream, okay. And then the point function says, okay, the next thing that my programmer gives me is going to be the actual attribute. And then the next thing that my programmer gives me is the point number, right? So we're using these parentheses for this thing. So it makes sense that we're kind of doing something different up here, right? So we don't want to use the same symbols. That could be potentially problematic and cause unreliable behavior. So somewhere along the line, basically whoever created this language just said, hey, for vectors, we know we need a bento box. We already use parentheses. Curly bracket seems like a good thing to me. Let's go with it, right? So that's kind of why we use the curly brackets. So anyway, that is a long and probably too detailed explanation of data types, but I doubt you will ever be confused about a data type ever again after watching this video. At least I hope. That's my hope. And if you still are, it's okay. It's probably my fault. But I think when we think about how we use this in our actual work, because a lot of times what happens is you'll go to make a move and you'll be like, do I need an integer or a float or a vector? And if you just really kind of stop and think about it, you can usually get the answer. Like, for example, if I want to know how many particles are in my simulation, if I want to do something with that, you could sit there and be like, does a vector make sense? Like, I don't need to know the direction that my particles are in, right? Now, if we're talking about velocity, well, hey, direction sounds pretty good for that, right? So maybe a vector for velocity, right? And in fact, you'll see that velocities are of the vector data type. But if we're talking about how many of something, well, it would make sense to use an integer, right? Because I don't want to have 200 million and a half particles. I want to have 200 million, or 100 million, or 10,000, right? I don't want 100.375 repeating particles. I don't want that. I want an integer, right? So that's pretty clear. When you're talking about a group, if you're trying to think about, what do I want to name this group? Okay, name. Well, I want to give it a name that is something that will help the animator realize what it is. So I'll call it the foot group. Let's say I'm rigging something, right? Well, foot's a word, so it probably can't be an integer, it probably can't be a vector, and it probably can't be a float, right? So it's got to be a string, right? It makes sense. A string, we use strings for words, right? So you see, it really comes down to it's the old maxim form follows function, right? Where like what you're using it for will really be like a bolt of light as far as understanding what data type you need to use. So the next time you're watching a Houdini tutorial and someone pulls out a vector, you'll know, aha, they need something with a direction and a magnitude, like maybe a position, right? Color's weird because describing why a direction and a magnitude describes color is actually kind of tricky. I don't really have time for it in this video, but trust me, it does work. But then like a normal would be another thing that makes sense to use a vector on, right? Because we're talking about a direction and then how strong in that direction. So hopefully that makes sense. It's a nice thorough review of all the data types, and I hope this was helpful.